Hello everyone. Welcome back to my course Fundamentals of Thermodynamics, Essential Knowledge for Engineers. In this video, we will talk about Introduction to Propulsion. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comments section or reach out to me via the email provided in my profile. Propulsion. The term propulsion comes from two Latin words, pro meaning forward and pellere meaning to drive. In essence, propulsion refers to the act of pushing or driving something forward. A propulsion system is a mechanism or machine that generates the force, known as thrust, needed to move an object ahead. In the case of airplanes, thrust is most often created through the application of Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. When a gas or working fluid is accelerated by an engine, the reaction to this acceleration exerts a forward force on the engine itself, propelling the aircraft through the air. A general derivation of the thrust equation reveals that the thrust produced by an engine depends mainly on two factors: the mass flow rate of the gas moving through the engine and the exit velocity of that gas as it leaves the system. Different propulsion technologies achieve thrust in slightly different ways, depending on how they handle the working fluid. In this course, we will explore four main types of propulsion systems used in aviation and space travel: the propeller, the turbine or jet, engine, the ramjet, and the rocket. Each of these systems operates on the same physical principles, but is optimized for different performance requirements and flight conditions. You might wonder why there are so many types of engines. To understand this, it helps to recall Newton's first law of motion, which tells us that an object in motion will remain in motion unless acted upon by an external force. For an airplane, this means that its propulsion system must perform two essential tasks. First, it must produce enough thrust to counteract drag, the air resistance that opposes motion, so the airplane can maintain steady, level flight during cruising. Second, it must generate more thrust than drag when acceleration is required, such as during takeoff or climbing. The difference between thrust and drag is known as excess thrust, and it determines how quickly an aircraft can accelerate. Different types of aircraft have different propulsion needs. For example, airliners and cargo planes spend most of their operational time cruising at steady speeds and altitudes. For these aircraft, high fuel efficiency and low operational costs are far more important than rapid acceleration. Since thrust depends on both the amount of gas moved and its velocity, engineers can achieve the same thrust either by accelerating a small mass of gas to a very high speed or by accelerating a large mass of gas to a lower speed. Propellers and turbofan engines are more efficient at moving a large volume of air at a lower velocity, which makes them ideal for commercial and cargo aircraft. This is why we commonly see high bypass turbofans and turboprops on these planes. They provide good thrust with excellent fuel economy. On the other hand, fighter jets and high-speed experimental aircraft are designed with very different priorities. They require rapid acceleration and the ability to overcome the enormous drag forces that occur at high speeds. In these cases, engine efficiency takes a backseat to maximum thrust output. To achieve this, military aircraft often use afterburning turbojets, which inject additional fuel into the exhaust stream to dramatically increase thrust for short bursts of high performance. Looking to the future, hypersonic aircraft, vehicles capable of traveling at speeds greater than 5 times the speed of sound, are expected to rely on advanced propulsion systems such as ramjets or rocket engines. which are capable of operating efficiently at extremely high velocities. Let's go step by step and learn about each of them. Thrust is the fundamental force that propels an aircraft forward through the air. It is generated by the aircraft's propulsion system, which can take several different forms depending on the type of engine used. Regardless of the design, all propulsion systems operate based on Newton's third law of motion, the principle of action and reaction. When a gas is accelerated in one direction by the propulsion system, an equal and opposite reaction occurs, producing a forward force on the engine and consequently moving the aircraft ahead. The thrust equation, derived from basic physical principles, shows that the amount of thrust generated by an engine depends primarily on two factors: the mass flow rate of the gas passing through the engine and the velocity of that gas as it exits. Rocket propulsion. During and after World War II, engineers and scientists began experimenting with rocket-powered aircraft to explore flight at extremely high speeds. Some of the most famous examples include the Bell X-1, which was the first aircraft to break the sound barrier, and the X-15, an experimental plane designed for near-space flight. These aircraft used rocket engines, which operate very differently from jet engines. In a rocket engine, both the fuel and the oxidizer, the source of oxygen needed for combustion, are stored on board. These components are combined and burned in a combustion chamber, producing extremely hot gases. The gases are then expelled through a nozzle, which accelerates them to very high speeds, generating thrust. Unlike jet engines or propellers, which rely on the surrounding air as a working fluid, a rocket carries all of its propellant internally. The hot exhaust gases themselves serve as the working fluid that provides the reaction force. This self-contained system is what allows rockets to function in the vacuum of space, where there is no atmospheric air. In contrast, jet engines and propellers cannot operate in space because they depend on the atmosphere to supply the oxygen needed for combustion and to push against for thrust generation. Rocket engines are generally divided into two main categories: liquid-fueled rockets and solid-fueled rockets. In a liquid rocket, the fuel and oxidizer are stored separately in tanks and are pumped into the combustion chamber as needed. This setup allows for precise control over the engine's performance. The thrust can be increased, reduced, or even completely stopped simply by regulating or shutting off the flow of fuel. However, liquid rockets are more complex, requiring pumps, valves, and cooling systems to operate safely. They are also typically heavier, and the fuel is often loaded into the rocket shortly before launch to minimize risks. In contrast, a solid rocket has its fuel and oxidizer mixed together into a single solid block known as the propellant grain. This solid propellant is stable under normal conditions and will not burn until it is ignited. When an igniter provides a source of heat, combustion begins at one end of the propellant, producing hot gases that escape through the nozzle to create thrust. The burning process moves steadily through the propellant, forming what is called a flame front. Once ignition occurs, the combustion continues until all the propellant is consumed, meaning that the thrust cannot be turned off or controlled mid-flight. To stop a solid rocket's operation, the only option would be to destroy the casing, which is obviously not practical. Although solid rockets lack controllability, they are simpler, lighter, easier to handle, and can remain ready for use for years without maintenance, which makes them ideal for missiles and booster stages in space missions. In the image, one shows the X-15 rocket-powered aircraft, and the other displays a rocket engine test. In the test image, we can see the rocket nozzle's exterior with intensely hot exhaust gases blasting out of the bottom. The X-15, flown by a single pilot, achieved incredible performance milestones. It reached altitudes over 60 miles, about 100 kilometers, above the Earth and flew at speeds exceeding 6 times the speed of sound, Mach 6, an extraordinary accomplishment achieved decades ago. Even today, only spacecraft such as the Space Shuttle have surpassed the X-15's combined altitude and speed records. This exploration of rocket propulsion illustrates how the principles of physics, especially Newton's laws, enable machines to reach the edge of space and beyond, marking some of the greatest achievements in human engineering and aeronautical science. Propeller propulsion. For roughly 40 years, following the Wright brothers' historic first flight in 1903, airplanes primarily relied on internal combustion engines to drive propellers and produce thrust. This same principle is still widely used today in most general aviation and private aircraft, which continue to be powered by piston engines similar in concept to those found in automobiles. The operation of such an engine begins when air from the surroundings is drawn into the engine, mixed with fuel, and ignited within a combustion chamber. The burning fuel releases energy in the form of expanding hot gases, which push a piston connected to a crankshaft. In a car, this crankshaft transfers energy to the wheels, causing them to rotate and move the vehicle forward. In an airplane, however, the crankshaft is connected to a propeller, and its rotation drives the propeller blades, which in turn generate thrust to propel the aircraft through the air. Propellers as airfoils. Although propellers may seem mechanically simple, the physics behind their operation is quite complex. A propeller can be thought of as a rotating wing. It generates a lifting force that acts in the forward direction rather than upward. The thrust comes from the air that flows through the propeller, not from the small amount of air used for combustion in the engine. The surrounding air is accelerated backward by the spinning blades, and according to Newton's third law, this backward acceleration produces an equal and opposite reaction that pushes the airplane forward. Each blade of a propeller acts as an airfoil, just like an airplane wing. When you look at a cross-section of a propeller blade, cut perpendicular to its length, you will see a typical airfoil shape, curved on one side and flatter on the other. Propellers usually have between 2 and 6 blades, and these blades are long, thin, and carefully shaped to ensure aerodynamic efficiency. Because the blades rotate around the central hub, the tips move much faster than the intersections near the hub. To maintain an efficient angle of attack, the angle between the blade's chord line and the oncoming airflow, the blades are twisted along their length. The inner portions of the blade, which move slower, have a higher angle of attack, while the tips, which move faster, have a lower angle. This twist ensures that the propeller produces a consistent and efficient amount of thrust along the entire length of each blade. Propeller testing has long been an essential part of aerodynamic research. For example, engineers at NASA's Glenn Research Center have tested numerous propeller designs in wind tunnels to study airflow, thrust generation, and efficiency. Similarly, propeller-driven aircraft such as the P-51 Mustang from World War II demonstrate how effective this technology can be when optimized for performance. Other engines that drive propellers. While early aircraft like the P-51 used traditional piston engines, aviation technology evolved significantly after World War II. As jet engines became more common, engineers developed a hybrid propulsion system known as the turboprop. In a turboprop engine, a gas turbine replaces the piston engine to spin the propeller. The turbine extracts energy from high-speed exhaust gases and uses that power to turn the propeller through a reduction gearbox. Aircraft such as the C-130 Hercules, a military transport plane, use turboprop engines. In these aircraft, most of the thrust still comes from the propeller, but the turbine engine provides the mechanical energy to drive it. Interestingly, even human-powered aircraft, such as those built during the 1980s, used propellers to achieve flight. In these cases, the engine was literally a person pedaling a system of gears connected to the propeller. Although the speeds were extremely low and the flights brief, these aircraft beautifully demonstrated how efficient propeller-based propulsion can be when designed carefully. In summary, propellers are a timeless and efficient means of generating thrust. Whether driven by a piston engine, a turbine, or even human power, the principle remains the same. Air is accelerated backward, and the aircraft moves forward in response. This elegant simplicity is why propeller-driven flight continues to play such a vital role in aviation, even in the age of high-speed jets and rockets. Gas turbine propulsion. During World War II, a revolutionary new type of aircraft engine was developed almost simultaneously in Germany and England, the gas turbine engine, which we commonly refer to today as the jet engine. This invention marked a major turning point in aviation history. The earliest jet engines functioned on principles similar to rocket engines, generating a hot exhaust gas that was expelled through a nozzle to produce thrust. However, unlike rocket engines, which must carry both fuel and oxidizer to operate, the gas turbine engine draws its oxygen directly from the surrounding atmosphere. This fundamental difference makes jet engines far more efficient for atmospheric flight, but also means they cannot function in outer space, where there is no air to supply oxygen for combustion. In a gas turbine engine, the accelerated gas that produces thrust is the jet exhaust, and most of the mass in that exhaust comes from the air entering the engine, not from the fuel itself. This makes the jet engine ideal for aircraft, as it efficiently uses the atmosphere as both an oxygen source and a working fluid. Today, nearly all modern passenger and military aircraft rely on gas turbine engines for propulsion. Because of their enormous importance to modern transportation and defense, understanding how jet engines work is a key part of studying propulsion. Gas turbine parts. Most modern passenger and military aircraft are powered by gas turbine engines, commonly referred to as jet engines. These engines come in a wide variety of shapes and sizes, reflecting the diverse missions and performance requirements of different aircraft. Despite these variations, all gas turbine engines share the same basic components and follow similar operating principles. A jet engine begins with an air intake or inlet, which brings in surrounding air. This air is then compressed by a multi-stage compressor, increasing its pressure, which is colored cyan. The compressor is connected to a turbine, which is colored magenta, by a central shaft, which is colored blue. The turbine extracts energy from the hot gases produced during combustion to drive the compressor and other components. Both the compressor and turbine consist of multiple rows of airfoil-shaped blades. Some of these rows rotate at high speeds and are called rotors, while the stationary rows are called stators. The combination of the shaft, compressor, and turbine is referred to as the turbomachinery. Between the compressor and turbine lies the combustion chamber, which is colored red, where fuel is injected and burned with the compressed air. This process generates high-energy exhaust gases, which then pass through the turbine and are expelled through a nozzle. The nozzle serves two primary functions. It accelerates the exhaust gases to produce thrust and regulates the mass flow through the engine. The thrust generated by a jet engine follows Newton's third law of motion. The backward acceleration of gases produces a forward reaction force that propels the aircraft. For example, the Pratt & Whitney F-100 engine, used in F-15 and F-16 fighter jets, illustrates the complexity of a modern jet engine. The front section brings in air through the inlet, which is part of the aircraft's airframe. The compressor, turbine, and combustion section work together to generate energy and accelerate gases. Some engines, like the F-100 afterburning turbofan, include additional components such as a fan section at the front and flame holders in the nozzle for the afterburner, which is colored orange. While visually intricate, the underlying principles, intake, compression, combustion, expansion through the turbine, and acceleration through the nozzle, are consistent across all jet engines. To help you understand how all the parts of a jet engine work together, we can use a computer model of a basic turbojet engine. In this animated model, you can look inside the engine and see the individual components in detail. For clarity, the parts are color-coded. The compressor is shown in cyan, the turbine in magenta, the combustion section or burner in red, and the shaft connecting them in blue. If the engine has an afterburner, the flame holders are usually highlighted in orange. As you watch the animation, you can see how the rotors and stators in the compressor and turbine work together, how fuel and air are mixed and burned in the combustion chamber, and how the hot gases are accelerated through the nozzle to generate thrust. You can also use the exploded view feature to see how all the pieces fit together, which gives you a much clearer picture of how the engine operates as a whole. In summary, jet engines operate by continuously drawing in air, compressing it, burning fuel to increase energy, and expelling hot gases at high velocity. This process produces thrust that powers aircraft, enabling them to fly efficiently at high speeds and altitudes. Using animated models helps learners visualize these processes and understand how all the components of a jet engine work together to make modern aviation possible. To better understand how engine design is linked to aircraft function, consider several examples of jet-powered airplanes, each with a unique purpose and corresponding propulsion system. At the upper left of the reference slide is a DC-8 airliner designed to carry large numbers of passengers or heavy cargo over long distances at high speeds. Because it spends most of its flight time cruising efficiently at altitude, it uses 4 high-bypass turbofan engines. In these engines, a large fan at the front moves a substantial volume of air around the core engine, providing efficient thrust and reducing fuel consumption, ideal for commercial aviation. At the lower left is an F-14 fighter jet, an aircraft built for air-to-air combat. While it also spends some time in cruise flight, its mission demands rapid acceleration and the ability to generate large amounts of thrust for short bursts during combat maneuvers. To achieve this, it uses 2 afterburning low-bypass turbofan engines. These engines can inject extra fuel into the exhaust stream, igniting it to produce dramatically increased thrust, a feature known as afterburning. This system allows the F-14 to reach supersonic speeds, though it consumes fuel at a much higher rate. At the lower right, we see a C-130 cargo aircraft. Like the DC-8, its main role is long-distance transport of heavy loads, but it does not require the same high speeds. Instead, the C-130 prioritizes reliability, fuel efficiency, and short takeoff and landing performance, which makes it highly versatile for military and humanitarian missions. It is powered by 4 turboprop engines, where turbine engines drive large propellers to generate most of the thrust. This design combines the power of a turbine with the efficiency of a propeller, making the C-130 particularly well suited for medium-speed, long-endurance missions. Finally, at the upper right, there is the T-38 trainer jet, an aircraft used to teach new pilots how to fly high-performance jet aircraft. Because it is designed primarily for training rather than combat, it does not require the extreme thrust levels of a fighter like the F-14. The T-38 uses 2 turbojet engines, a simpler and lighter type of gas turbine engine that provides smooth, predictable performance, ideal for teaching pilots the fundamentals of jet flight. Each of these aircraft demonstrates how variations in gas turbine technology serve different operational goals. Whether prioritizing speed, efficiency, or power, engineers tailor the basic principles of the jet engine to meet specific flight requirements. This adaptability is what has made gas turbine propulsion one of the most successful and enduring technologies in the history of aviation. Okay guys, now let's have a little quiz. The quiz consists of 5 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. What is the primary principle behind all propulsion systems? The correct answer is Newton's third law of motion. Question 2. Which of the following is a key difference between rocket engines and jet engines? The correct answer is rockets carry both fuel and oxidizer on board, while jets use atmospheric oxygen. Question 3. Why are high bypass turbofan engines commonly used in commercial airliners? The correct answer is they are highly fuel efficient. Question 4. In a propeller, why are the blades twisted along their length? The correct answer is to maintain an efficient angle of attack along the entire blade. Question 5. Which type of engine allows precise control over thrust by regulating fuel flow? The correct answer is liquid-fueled rocket. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics and Structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with aerospace engineering, avionics, and aerospace systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about understanding thrust, the power behind flight. See you in the next video. Bye.